Hello, and welcome to the Landscape Technology Review Guide for our final exam in our course. Real quick, before we get started, some quick notes on how to use this guide. It's a video on YouTube, so feel free to watch it however many times you want. You can use the faster playback setting on YouTube to speed up the watching process, so you don't have to sit through this however long it ends up being, an hour or 2 hours. It will be a detailed overview of the entire final exam, but most importantly, this guide will not replace the readings that you find on Box. And so I highly recommend that everyone still stick to the readings that you find on Box. And also what's important as well is I'm going to take this video down on April 13th, 2020. The reasons being is I don't want it to be used on the exam. So that's why I have to take it down at that time. So the first issue that we need to review is how do you actually get licensed as a professional landscape architect, the PLA designation. And so the question is, why should you get licensed to begin with? The first thing to know is, what does licensure actually mean? Licensure really means that you can demonstrate minimum professional competency. It does not necessarily mean that you have 100% fully mastered the profession. It just means that basically you have a baseline level of knowledge that you can use in order to safely practice this profession. And the key point here is that it's qualifications that help you practice landscape architecture that positively impact the health, safety, and welfare of the public. Health, safety, and welfare, or HSW, is considered to be by many the primary responsibility of landscape architects and architects as well. And this will be emphasized over and over again as part of your career. Depending on where you work, licensure is going to be required in order to approve construction drawings. This is what's known as stamping drawings. And so if you decide to work in a certain state and do projects in a certain state, you need to be sure that you're licensed in that state in order to actually build projects there. And licensure also opens up the door to individual practice. What I mean by that is freelancing, or if you want to start your own firm, getting licensed begins to open the door to that potential avenue, should you want that. And then last is a piece of advice to everybody is that you should try to get licensed as early as you can, immediately after graduation. So once you finish school, you should start thinking about how to get licensed and prepare for that as soon as you can, because it really is no benefit to waiting in terms of this. In order to start your licensing process, you need to think about where you end up working. And so depending on which state you end up working in, you're going to have a slightly different list of requirements that you need to fulfill. But generally speaking, there are some requirements that are the same regardless of which state you ended up working at. And this is kind of what you should expect to fulfill in order to become licensed. The first, obviously, graduate from an accredited school of landscape architecture, such as WashU. Second, you need at least 3 years of professional working experience. Those 3 years must be under the supervision of a licensed landscape architect, a licensed architect, or a licensed engineer. In some states, doing teaching or research at an approved university, that can count towards professional experience, should you choose to do teaching as part of your career path. And then the last point, obviously, you need to pass all 4 sections of the LARE, the Landscape Architect Registration Exam. So what I'm going to do now is I'm going to cover the LARE, the overview of the test, and talk about what you can expect on each test and how do you prepare for each test. And then also, where does landscape technology, our class, fit within that? Section 1, this is the project and construction management section. This is topics that relate to construction contracts, the bidding process, the construction administration process, and also a project management level, like understanding how to actually run a firm. And this is topics that are typically taught in the pro practice class. So I don't know if you guys have taken that yet, but this is what that class is meant to prepare you guys for, is section 1. Section 2, this is the inventory and analysis course, or analysis test. And this is all about understanding how to look at a site and begin to dissect it and begin to think about how you can take a site apart and understand how to use the existing site conditions in order to design on top of it. And so this is stuff that you typically prepare for in your GIS class, in an environmental systems class, and a lot of other technical level classes. I would say grading and even a little bit of this class help prepare for that as well. Section 3, this is all about the design aspect of landscape architecture. And so a lot of this material is things that you actually practice regularly because it's stuff that you need to do in studio. And so with the work you do in studio in terms of master planning, doing site design, doing getting community feedback, this is stuff that you practice in studio, but also representation as well, because a lot of this content is about figuring out how you can use visuals and illustrations to communicate design intent. So design representation is a huge part of section 3. And also I'll throw in planting design as well, because planting design is a part of this section. Section 4, this is all about technical documentation, grading, and drainage. And so this section 4, this is what landscape technology is for. This is the section that I'm helping you guys prepare for. It's really all about documentation, putting together plans, putting together details, and understand how the whole construction documentation process comes together. And so this is material that you're learning in this class, but also grading and landform, and a little bit of pro practice as well. And so what I need to quickly just clarify is that everything that you see in this review video will be content that you could potentially find on section 4 of the LARE. But not everything in section 4 is covered in this video. There's a lot of content on section 4 that you're not going to learn in landscape technology. So, but that being said, the way this class is organized is I'm trying to put as much of the important topics that I found to be prevalent on the exam as part of this class. A lot of the topics that I'm skipping over are not hugely tested topics on the exam. And so a lot of what landscape technology is the major buckets of things that you will need to prepare for in order to take the test. But obviously the best way to prepare for this exam is to simply work as a landscape architect for several years after graduation. So the first section that we're going to cover is the design documentation aspect of the class. This is important because this is actually something that's heavily tested on the LARE. And so I write down here at least 20% of the questions that you see on the LRE section 4 will be about design documentation. And also as a side note, I am writing down the actual readings that you need to reference right here below the title. And so if you want to get in more detail on the topics that I'm presenting in this video here, you should reference these specific readings to get more detail on that. The first thing that we need to go over are the standard phases of the design process. This is important because understanding this helps understand the role of the landscape architect and also, more importantly, the role of the actual drawings themselves at each phase of the design process. And so this list of phases here, this is stuff that you probably know by now, but you should understand that at each phase, the drawings you produce are a little bit different. And the reason it's a little bit different is because you have a different audience at each phase. And so real brief, I'm going to go over that again. This is stuff that I presented early on in the semester. The first phase is concept design. This is all about having the big idea and the big design intent for your project. What's important here is that really what you're trying to do is you're trying to convince the client to go with the big idea and the big general direction of the design project. So really what you're trying to do here is you're trying to propose like the big concept that the client can support. And overall, it should be a practical idea, but it's also important to think of this stage as a platform to kind of propose some cool, interesting, wild ideas, anything that you can think of, because one thing that I like to describe this phase as is kind of like your war chest phase. What I mean by that is basically, if you think about it, at later stages of the project, just due to simply budget cuts and that whole process, things will get eventually cut. But if you start with a high level design concept where you actually have a lot going on, as the project gets cut, you're not cutting away from something that was already too simple to begin with. You're cutting from something that was a very high design idea. And so stuffing your war chest or making this a really packed, a really fully realized design idea is important because as the project gets cut, you're going to be cutting from a high level of design, a high level design, as opposed to like a simple design. So this is kind of like the overview of a concept design. This is something that I would say most students in school are very familiar with. In fact, I would say 90% of design projects in school only end up at the conceptual design phase, which is fine for school students. In some classes, you might take a design up to the schematic design level. This is very rare because this involves taking design and bring it into a level of detail where you can actually begin to think about it, the constructability of it. Now, that being said, the schematic design is still at this phase all about conveying a design concept using illustrative graphics and beautiful drawings. What I write here is that the audience of this project is not just a client, but it's also stakeholders, community members, potential donors who can pay for the project, the potential audience and users of the actual project. And really what you're doing here is you're using the drawings to help gain excitement and support for this design proposal. What's key is that what you're showing in your site plans at the SD phase is a resolved design concept. It should have the big questions answered in terms of the grading that you're doing, the planting that you're using, and the material choices that you're making here. Maybe it's not fully detailed yet, but you should have a resolved idea, a big idea resolved at the SD phase. Now, a SD level set does not have enough detail to be implementable, meaning it doesn't have enough detail to give to a contractor and they can build it. So it's still high level, but it can be used for cost estimates, which means you can take this and kind of like look at the site plan and begin to think, all right, it has this much square feet of concrete paving, this much square feet of lawn, and then you can use a multiplier to begin to come up with a high level cost estimate. So that's the SD phase. And then the following phase will be the design development phase. And this is considered to be by many landscape architects the most important phase of the design process, because this is when you begin to really translate the design concept into something that is implementable. Implementable meaning, again, something that can be built by a contractor. Now, what's critical is that here you're still making design decisions, right? But the design decisions are detailed design decisions, all about how do you actually put the elements of your project together and actually come up with the actual details. And so here you begin to examine the physical relationships, between elements, materials, systems, all about the project. And then at this phase is also the phase that you're beginning to lay out the sheets for your project, the drawing package for your project, in order to begin to get a high level view of what drawings are required in order to fulfill the final drawing package. So this is the level of detail that I'm trying to focus as part of our class, the DD level. And the drawings that we're doing in this class are all trying to achieve this level of detail at the design phase. What I write down here, the best way to learn how to produce DD drawings is through professional practice. I try to bring some of that to this class, but also a good way to learn DD level drawings is to work on, say, design build studios or even furniture design studios where you need to actually begin to think about how things come together and how you actually build things. So the last phase of the documentation process is construction documents. And so this is the critical phase where the drawing transitions from a design document into an actual document that is used by contractors. And so the main audience at the CD phase is contractors, and I'll get into that in a second. These drawings, they're used for the process of the bidding phase, And this is purely about implementation. Everything about this package is just about conveying the information to the contractor so they can understand how to build your project. And so this is the final stage of putting together a package. And what I write down here is that really the only way to learn CDs is just simply work, because a CD only counts as a CD if it can get approved or stamped by a licensed landscape architect. So you actually need to work for a licensed landscape architect in order to actually work on a CD drawing set. So again, reviewing the critical aspect of the DD and CD level, the primary audience at these phases is contractors. The contractor is the party that is responsible for building your project. Why? Because at this phase, after these phases, the contractor is responsible for these aspects: project bidding and constructing your project. And they need to be able to understand how to achieve these two aspects, and they can only understand those through the way we put the documents together. The combination of a site layout plan, a grading plan, and a materials plan will give a contractor sufficient information to estimate material quantities and thus estimate the cost of a project. This is really the key point here, is that the final construction documents are meant to put together enough information so that a contractor can tell you and tell the client how much it costs to build the thing. And then that's called a bid. And that bid goes out, and then the client decides, usually they select the lowest bidder, though on certain public projects, they will have to select the lowest bidder. That's not always required on private projects, but that's kind of where you want to get to. You want to get to a point where you can actually begin to price the project. And so the combination of these drawings here helps you achieve that. So next is understanding what is included in a set of construction contract documents. This is a little bit different from the actual CDs themselves, but what is included in the whole package of documents? And there's two major things. The first are the actual drawings themselves. So the drawings, these are the blueprints, the visual instructions, and quite literally they depict graphically, using lines, numbers, points, the characteristics, and the extent of the project. It tells you what is involved, where it's located, and what are the physical dimensions of the project. And so typically the majority of the work that you do when you're putting together a project is the drawings themselves. But the other part of this package is what's known as the technical specifications, otherwise known as the specs. And these describe in words the characteristics of your project. Specifically, they talk about what the materials you're using are, how they are intended to function, and where you can acquire the materials. They cover qualitative aspects of the project that aren't easily described in drawings, and they also cover aspects of execution, workmanship, and how to prepare the project site in order to get it ready for project implementation. So one key point here is that in the event of a discrepancy between the drawings and the specs will take precedence. And this is what's known as the specs govern. And this is established as kind of like an order of priority in the general conditions of a set of contract documents, where basically they say, if a contractor comes across an error where they see a discrepancy or a difference between what's drawn and what's written in the specs, typically they'll put the specs on top of the drawings. And this is more just an industry standard way of having a unified approach to this. And so again, the main point here is that, again, when you understand that there's a conflict between these two things, that the specs will usually be the one that wins out. Now, minor sidebar here on technical specifications. And I put this sidebar here because I know as part of landscape technology, I didn't really cover technical specifications that much. What I need to mention here is that technical specifications is a heavily tested aspect of the LARE, and you will need to know a lot about that in order to successfully become a landscape architect. But as part of my version of this course, I've chosen to not go into too much detail on this topic due to its complexity. And so all I really want to say is that when you prepare for the real test, you will have to prepare and understand more about technical specifications. And this kind of goes back to one of my initial points early, is that not everything on section 4 is going to be covered in this video. And this is one of the things that I'm not testing as part of this class. Again, the reason I don't test this is because it's highly complex, and it's something that really makes more sense when you actually begin to work on projects at a firm and you're actually putting stuff together. In school, this is not stuff that you need to get bogged down on. In school, really what you need to worry more about is like coming up with cool ideas and creative design ideas and putting that stuff together. So that's the only reason why we don't talk about technical specifications that much in class. Just be aware that it's extremely important. Okay, so what drawings do you find in a typical landscape documentation set? So this is what you find in a typical package, and I'm going to go through each one of these in detail momentarily. So, but what's important to understand is that the sheet order of a documentation set, it typically follows the order of site construction operations. And generally it should go from a high level amount of information at the beginning and move towards a more detailed level of information near the end. What I mean by site operations, this right here, is that when you look at the order of this documentation set here, this sheet list, the first sheets are kind of like the early stages of the design process, where, for instance, you would start with protecting your trees or demoing the site, and then from there you begin to lay the site out, add the materials, work on the grading, and then the last couple of elements of the site construction process relate to things like adding planting and soils, because that's really the last stage of the design or the construction process. That's what I mean by this here. The order of the documentation step would follow the order of site operations. So, going into more detail, let's look at each of the drawing sheets. First is the cover sheet. This identifies all the key project identification information. It talks about the document set description. In this case, for this example that you see here, this is known as a city submittal. This also could refer to the phase of the document, where it's at in the design process. So, for instance, there might be something like called a 60% DD phase or a 50% CD phase, basically a progress print of the documentation set that's given to the client in order for them to review. Obviously, has a project title. It needs a project owner who's actually paying you to put the drawings together. It needs the project teams. Every consultant that's adding a drawing to this package should be recognized in the title block here. You obviously need a location and address where the project is located. Sometimes on a cover sheet you have a location map. This example on the side does not have one, but a lot of times it will have one. An issue date. This is typically located as a revision panel on the title block here. Basically, like, when you submit a drawing package, it needs an issue date, basically a date to describe when you issued it. A sheet index. This is basically your table of contents, extremely important because it gives a contractor at a glance all the sheets that are actually part of your package. And obviously a project illustration to show what the project looks like. One of the first drawings that you will have as part of your construction drawing landscape documentation set would be a site reference plan. This plan shows a holistic view of the existing site and its proposed conditions. This is one of the few sheets in the entire project package that actually shows the entire project on a single sheet. And so that's the key point of this one, is because landscape projects tend to be pretty large in scale. And so it's really usually kind of difficult to put, a package together with one plan on one sheet at a time. And so the reference plan does this, and it also begins to delineate where the breaks in the sheets happen. So this is shown here. For instance, this site plan here is being broken out into 4 quadrants, and it's using this dotted line here as it's known as a match line. This dotted line here begins to break out the various areas of your site plan. So that's the site reference plan. And then next would be the existing conditions plan or a survey. This is pretty straightforward. This is a drawing that's provided to you guys by a civil engineer or a surveyor. And this will illustrate some very basic existing condition information, such as the legal property boundary, the site topography, the vegetation, soils, hydrology, utilities, structures, circulation, easements, and right-of-ways on site. So pretty straightforward. The next plan is going to be the tree protection and removal plan. This is a really important drawing for landscape architects to put together because what you're doing here is you're identifying which trees you need to remove, and more importantly, what trees you're choosing to protect as part of the project. Now, in order to do this, you need to illustrate on the drawing what's known as a critical root zone, which is basically a circle that is a kind of an estimate of the the roots of the tree. This is also known as the drip line of tree. This circle is generally acquired using a multiplier of the tree caliper itself. And so what's critical about this circle here is that basically you don't want to have any cut and fill in this area. You don't want to have any storage of materials in this area during construction. You don't want to have any construction traffic going over the critical root zone at any time, because what that does is obviously is it creates compaction in the soil, and that will adversely affect the tree health. It might even kill the tree. In addition to that, the tree protection and removal plan would typically illustrate a tree protection fence. And so what that might look like is on a plan, you might have a critical root zone like this, and there might be a fence line drawn around that to basically illustrate on the construction site that this is an area you don't want to have any construction traffic going on. So that is this one. Again, the tree protection plan actually is one of the more important plans as part of your jobs, and I say this all the time, is that your job as a landscape architect is really to protect as many trees as you can, because the client or anyone else who doesn't understand the value of what trees provide on a site, they will not hesitate one bit to cut down a tree. And so what we need to do is we need to actually use this as an opportunity to protect and as many trees as we can on a site in order to preserve the inherent value of those trees. The next plan that we're going to review is the demolition plan. The demo plan, it identifies all the site items that are meant to be protected, removed, recycled, relocated, or salvaged on the site. It only focuses on hardscape, and that's different from the previous plan, which only focuses on vegetation. It should include reference notes that supplement the plans. So there's going to be a lot of specific instructions that you need to provide the contractor, and so this is where you provide reference notes. Say, for instance, you need to tell them to remove and stockpile existing pavers to be reused and dispose of broken pavers. This is a very common reference note that we use on projects where we want to reuse some existing paving that is not of poor quality, but we can reuse them. On projects with buildings, the plan should also show where access to the building is provided during construction. Though that being said as well, that this is also something that could be decided by the contractor themselves. And so I would say this is a fairly optional addition to the demo plan. What's most important about this is that it should avoid assumptions. What I mean by that is that unmarked materials on your plan here will be assumed by the contractor to be left as is. And so in order to avoid assumptions, make sure that your plan marks out and annotates everything on the site so that you can avoid having a mistake and an assumption. You want to be as comprehensive as you can in your instructions on what needs to stay and what needs to go on the demo plan. So avoid assumptions on the demo plan. The next plan is the materials plan. This defines literally what site hardscape design elements are to be built. So in a way, this is kind of like your basic site plan. Identifies all materials, components, systems, and finishes on a project. And it uses a simple system of symbols and hatches to distinguish site elements on your project. And so what I'm going to go through later in this presentation is how we do that. It typically uses a keynote system in order to begin to connect the materials to a detail within the project. And so I'm going to go over that later in this presentation. And then lastly, The materials plan, it should also locate the jointing patterns that you begin to propose on your paving and in your concrete as well. So a fairly straightforward plan, but very fundamental to the landscape design package. The next one is the layout plan, and this one defines where site hardscape elements are to be built using dimensions, angles, and other types of annotations that begin to like literally measure out the dimensions of elements on the site. It provides the horizontal position of site elements, and it works in conjunction with the materials plan. So on small projects, you can actually combine the layout plan and the materials plan in order to keep your sheets nice and consolidated so you don't have too many pages in your package. And also, we'll talk about dimensions later in this presentation as well. But typically for us in landscape architecture, we should be using the architectural scale dimensions, basically feet and inches. Again, we'll go over more about the layout plan later in this video. The next one is the grading plan. The grading plan establishes the position of site elements vertically, and it uses that through the system of contours and spot elevations that you guys all know about because you took grading in landform already, right? It identifies spot elevations of all exterior stairs, ramps, curbs, walls, and drainage structures. It also defines the direction of drainage and runoff on the site, meaning like where you are intending to divert runoff based off of the grading scheme. So obviously it uses contours and spot elevations. And also, this is also where you begin to indicate the elevations of stormwater BMPs that you're proposing on the site. And again, we will talk about stormwater management in more detail later in this presentation. Next is the planting plan. This is pretty straightforward for most people. All it is just basically identifying what plants and how many of each plant you are proposing on a site. It establishes the position, form, size, and species of proposed trees and planting on the site. And it should include a planting schedule as well that displays the plant counts as well as the plant name, genus, caliper sizes, spacing during installation, and any specific installation notes that you want the contractor to be aware of when putting this together. So this is a very simple, straightforward plan. One of the key points here, a contract document drawing should not imply any procedure on how to build the project, in whole or in part. What do we mean by this? Effectively, this means that we don't want to be telling the contractor how to do their job. Really, this is all about the relationship between the designer and the contractor. And so some notes here. You're not telling anyone how to build it. If you tell them how to build it, then you are liable for any errors or problems that may occur during that. What I mean by that is basically if you tell the contractor how to build the project and through that method that you tell them the project fails, that means the person who put the instructions together, or rather you who made the mistake of doing that, you are liable for that error. So you don't want to give the contractor the directive on how to build a thing. You want the contractor to decide for themselves how to actually build the project in the way that they want and in the order that they want, because that's their job at the end of the day. Contractors are concerned about the efficiency on construction, which is why you don't tell them how to do their job. And contractors like flexibility in material decisioning so they can choose competitive pricing. Now, this sounds like that you're giving the contractor full control over the project. That's not true. That's why there is a CA phase, construction administration phase of the project, where it's your job as landscape architect to approve the methods and the decisions that a contractor is using during construction. But really what the big picture here is that you don't over control the decisions of the contractor. You let them do their job. So again, really important point here. You don't tell the contractor how to build their project. So next will be the layout and materials plans. This is content that is part of the term project assignment. Basically, the term project is all about putting together your own layout and materials plan. The reason why this is pretty critical is that this is really one of the more fundamental drawings that you need to understand how to produce as part of a construction documentation package. So we're going to have a whole section dedicated just to these two plans. And we're also going to talk a little bit about dimensioning as well. So again, the layout plan, it establishes the horizontal position, orientation, and extents of all hardscape site elements. The materials plans, it defines what site hardscape elements need to be built. Key point here, when you're putting together your layout plan, underdimensioning results in greater interpretation by the contractor and loss of control by the designer. Overdimensioning, that leads to confusion and it implies inflexibility during construction. This is kind of what the plans are supposed to try to accomplish here, is that you want to preserve as much design intent as you can, but you don't want to confuse the contractor by over-dimensioning your plan. And I would say in general, it is actually better to slightly under-dimension rather than over-dimension, because you want to be a collaborator with your contractor and allow them to work on the project in a way that makes the most sense for the project without giving them so much constraint that they can't do their job best. So this is kind of what we need to figure out how to do as part of putting together layout plans. Another key point is that all dimensioning that you do on a project in the layout plan, it must start from a known reference point that is not to be disturbed or removed during construction. And what I mean by that is, like, for instance, when you're laying out your dimensions on the thing, it must be measured off of something that can be measured on site and found on site and will not move. And for example, it might be, say, for instance, a building corner or a building side or a street curb, something that is not going to be moved or disturbed during construction. It could also be an imaginary point or line that can be easily located in the field. And this could be something like a property line or even a road center line. And this is what's known as a point of beginning, also called a point of origin. And that's in this little example shown in the bottom left-hand corner right there. So this is a point that is part of the drawing that begins to help establish the overall layout of the plan. This is the starting point where all other dimensions branch off of. And so this is some examples of typical points of beginning that you could identify on a project. And then from there, you can begin to understand the different types of dimensions that you can use on a layout plan. So the first is going to be the fixed dimensions. And these are all about establishing lines that have a high degree of accuracy, because these lines are going to be lines that you base all other dimensions off of. So it's really critical that these fixed dimensions are dimensions that stay the same regardless of where you work and are consistent throughout the project. So examples include property lines, road center lines, right-of-way lines, building locations, and building setbacks. Semi-fixed dimensions. These are dimensions that are located in reference to the fixed dimensions. So this would include dimensioning things such as sidewalks, terraces, parking areas, walls, fences, and other landscape elements. Semi-fixed dimensions are probably going to be the majority of the dimensions on your layout plan, simply because they are usually all being referenced off of a solid fixed dimension, and that's perfectly fine. But then lastly, there is what's known as flexible dimensions. And these are dimensions that do not require such a high degree of accuracy, but it's important that you give a sense of the dimension to the contractor. These dimensions locate site elements that do not require perfect exactness. They measure items that may be adjusted and changed due to field conditions and that might arise during construction. Usually you indicate a flexible dimension with a plus or minus sign. And examples of site elements that you might measure with a flexible dimension should be things like planting areas or meandering walkways. So I'm showing this example right here of this curvilinear edge here as something that could be measured using flexible dimensions. And then the last type of dimension that's kind of related to a flexible dimension is a field dimension. And this is something that you can only determine after construction has progressed. So in terms of dimensioning, there is another key point, and that the implied precision of a dimension is always assumed to be 1/2 of the smallest unit indicated. So I have some examples that explain what I mean by that on the side here. So if on your dimension you have 10 feet as your dimension, what that means is that the precision of that dimension is plus or minus 1/2 foot, 6 inches. that is a lot of room for error there. You don't want to give the contractor that much flexibility on a project. A dimension of 10 feet 2 inches, that implies a precision of plus or minus half an inch. The reason that is because the smallest unit of your dimension is an inch, right? So if the smallest unit is an inch, the implied precision is half an inch. Going back to this first example, if it's 10 feet, that means the implied precision is plus or minus half a foot. So the way to fix this one here is actually to mention as 10 feet 0 inches. So now, even though that this and this are technically the same thing, because you're using the 0 inches here, the inches becomes the smallest unit. And so that implies a precision of plus or minus half an inch, which is good. You can go a little bit overboard with this as well. Sometimes you can say like a dimension of, say for instance, 10 feet 3.5 inch. The smallest unit here is actually half an inch. And so that implies a precision of plus or minus a quarter inch. That might be too detailed for a contractor. And so something like this should be avoided. So the next part is understanding the dimensioning systems that we need to use during a project. So the first system is the perpendicular offset system. This is a very widely used system in projects. It's a common, convenient method for site layout, especially for projects that have very simple orthogonal geometry. You can see on the example here, this project mainly uses orthogonal right angles to lay out this roof plaza space. So dimensions will run perpendicular or parallel to the fixed reference dimensions, such as the building edge or the property line. And when you do a dimensioning system like this, where you basically link a dimension from one edge to the next edge to the next edge, what you're doing is you're creating what's known as a string or a chain of dimensions. So again, this is a very simple, easy way to lay out dimensions on a site plan. The perpendicular offset system. A variation of that is what's known as the baseline system. This is typically used for curvilinear designs that maybe do not require a high degree of accuracy. And so what it is basically a series of offsets at fixed intervals that are taken off of a baseline at the edge of a proposed element. And so two examples here. The example on the bottom, the baseline system is using a series of dimensions that are at these 5 feet intervals along what appears to be a wall that begins to measure out the edge of this planting bed here. In the top example here, it's using a baseline through the center of this plaza and measuring off of that at perpendicular angles in order to measure out this curvilinear detention pond, as you can see here like that. So that's the baseline system, another way to lay out elements on the site plan. The coordinate system. This is a site dimensioning system that uses Cartesian x and y values to indicate a specific point on the site plan, using a system of northings and eastings, which I will explain next. Distances are indicated as a north or south or east and west based off a point of beginning. So what's missing from this little example here, in this image here, is a point in the lower left corner, where basically from that corner, if you go over in this, let's say it's this example right here, 5,000 something feet this direction and 4,000 something feet in that direction, you will find yourself at that point over there, depending on wherever this point is located here. The next dimensioning system that we typically use is what's known as angles and arcs. This is used for complex curvilinear geometry, but you want to, as opposed to, say, for instance, the baseline system, which is a very loosely measured curve, this one is a bit more of a precise curve. And so using angles and arcs, you can actually begin to lay out very complex geometry, like the one we showed at the start of this presentation. It requires defining the radius of an arc and the internal angle of the curve. And I'll explain that in the next slide. Most contractors appreciate layouts that are drawn using simple lines and arcs. Splines are like the really crazy looking curves that we do in studio all the time. These are really difficult to lay out with accuracy. And so whenever we want to bring a spline project into the actual construction phase, we want to be able to break this down into a series of angles and arcs. So a couple of examples. A symbol curve, number A right here. This is a single radius. As you can see, it's a simple line and an arc and a line. The next one would be a compound curve. This is a curve with two or more radiuses. You can see there's one radius here and another radius right here before it goes into the next tangent. A reverse curve, this simply reverses the direction of the angle. And then a broken back curve, this is simply two curves in the same direction that are connected by tangent. Imagine this is a single radius that was broken by a segment, and then that's how you do it. So this is a very simple system for dimensioning curvilinear objects, angles and arcs. Going back to the coordinate system, there is a definition that you need to understand, northing and easting. Northing, easting, this is the geographic coordinate of a point. Easting, the eastward measured distance from the x-coordinate, and northing, the northward measured distance from the y-coordinate. So this system here is related to the coordinate system that we talked about earlier. As you can see in this side plane here, we're using the northing and easting system to basically locate the corners of this walkway through this tree grove. This is actually City Garden, which has a very, very nice set of construction documents. So next we're going to cover a few graphic conventions that need to be understood in terms of dimensioning. These are things that I think people tend to take for granted, but we just need to review it because we see these mistakes time and time again where people dimension things randomly and they forget the very fundamental aspects of dimensioning. So first off, extension lines. So this square here, this is the object that is being dimensioned. The extension line is this line right here. And the dimension line is this one right here. And the extension line must always be at a right angle from the object that it's referencing. Let me change the color of this pointer so it's a little bit easier to see. So that line must be at a right angle to the dimension that it's referencing. This is the way it makes the most amount of sense, is that the extension line must always be perpendicular to the thing that it's referencing. Tick marks. You always need to use a tick mark when you are dimensioning things. So sometimes I see projects where there's a dimension line like this and there's no tick mark. You need a tick mark in order to indicate where the start of the extension line and the intersection of the dimension line starts and ends. So you need to use a tick mark. And here's a bunch of examples of ones that we use. The one that is the most common is this one right here, but you can just use a dot, you can use an arrow, whatever makes the most sense. It doesn't matter, but the tick mark is extremely important to help basically make the dimension much more clear. Hierarchy. A very common problem that I see is that people tend to put dimensions at various random angles, but not angles, but various distances away from the thing that's referencing. But you always want to make sure that the object that you're dimensioning is as close to the dimension as possible, and then overall dimensions are placed farther away. So you begin to see there's a hierarchy here where this overall dimension is at the furthest distance from the object as measuring. This is what we want to do. A mistake would be, say for instance, you had these dimensions here, and then you had this overall dimension right there. That creates confusion because then it begins to create this system where it's confusing where, for instance, this dimension line starts and ends. You never want to have that happen. Another very common error, dimension placement. You don't want to put a dimension within or inside an existing structure or a structure you're proposing on the site. That creates a little bit of confusion in terms of dimensioning things here. So you're going to see this is a poorly dimensioned series of site elements here because you're pulling the dimension extension line into the object itself where you don't need to create that amount of clutter. Speaking of clutter, dimension clutter. So basically, you want to avoid crossing dimension lines and extension lines since that creates too much clutter and it can create confusion for the contractor. Remember that clarity is the key to the effectiveness of a drawing. The goal is to communicate design intent as efficiently and accurately as possible. So this example I'm showing here, you can begin to see that there's a lot of dimension lines that begin to overlap with one another here, everywhere else. That is not good, not a good practice, is to have too many dimension lines overlap with one another. And then a final point here, a key point here, is that redundancy should be avoided. What I mean by redundancy is that redundancy is over annotating and over labeling your layout plan or material plan. Information is given only once and in the most logical place. There is this common misconception where basically if you think to yourself, oh, if I over annotate and I add a lot more labels to something on a site plan, that will basically reinforce the importance of that thing. But as I write here, duplication for reinforcement's sake is not a valid strategy. What duplication does is that if you have a change in the project later on, you need to change that for everywhere you duplicated it. And so that creates this possibility of creating some drawing errors because you don't want to be changing everything, so you might accidentally forget something. And so doing this actually is a really problematic thing. And so only give information one time and in the most logical place. Now, going into the materials plan in more detail, I mentioned this keynote system. This is something that I kind of brought up later in the course, but it's also pretty important. The keynote system is a very conventional system that is used in a lot of materials plans. It's a system that's used to establish a direct link between the graphic information that you see in the site plan and the details in the package. And this is a nice system to use because actually what it does is it cleans up and it brings clarity and simplicity to the layout plan. So you can see this example in the bottom here. There's not like a million labels of all the materials. You just use this very simple system of keynotes to actually make a very simple, clean plan that has a legend on the side that references the actual detail of the project and also where it's located on the project. So this is also an important note here is that this legend for this keynote system, it needs to be consistent for the entire set of documents from the materials plan to the site sections. So this legend here, if you use it for the materials plan, you need to use it for the site sections as well and have the same system of labels in order to maintain a consistent series of annotations. And then finally, one thing that I want to note about is hatch patterns. And I need to bring this up because in a lot of the drawings that I've seen from the student projects, was using a lot of inappropriate or non-standard hatch patterns. And so it's really important that you guys understand the real fundamental hatch patterns, specifically earth patterns, concrete patterns, metal patterns. You always want to make sure that you're using the right patterns when you are putting together your plans because not doing so, again, creates confusion. Contractors are generally speaking used to a general graphic style and look for these drawings, and you always want to make sure that you're using the right style for the right material that you're showing. So make sure you're using the right hatches for the right materials. The next subject that we need to talk about is stormwater management. Now, stormwater management is one of the more important subjects that we need to study and practice in order to prepare for professional work as a landscape architect. This is mainly due to the fact that right now our cities are growing fast, and there is as a result of that, there's a heavy increase in impervious surfaces on the planet. This is creating what is known as stormwater. Stormwater is water that moves on the ground by gravity and flows into our water bodies, such as our rivers, lakes, oceans. And what it's doing is it's basically carrying pollutants with it. So you imagine water hitting, say, the surface of a parking lot. It's carrying with it all the oil and grease and pollutants that drop onto the parking lot, and then it's carrying that into our various water bodies. And that's why it's called stormwater, is because it exists during heavy rain events and exists due to the fact that water cannot permeate into the ground. And if it can't permeate into the ground, it runs off, sheds off the surface and creates what's known as surface runoff. Stormwater management is important right now. It's emerging as one of the primary design responsibilities of landscape architects, mainly because of the reasons I just mentioned, urbanization and the disruption to the natural systems. Now, the current ways that we address this issue of stormwater management is what's known as a BMP, best management practices. These are basically techniques and measures that we use to control, storm, or treat stormwater runoff from developed areas for the purpose of reducing flooding or removing pollutants while maintaining or enhancing environmental quality. Like I said here, the goal of a BMP is to control non-point source pollutants. So what is the difference between a non-point and a point source? Non-point source is basically pollution that's caused by rainfall carrying on the ground human-made pollutants such as fertilizers, herbicides, oil, grease, sediment, salt, bacteria, pet waste. And whereas point source pollutants are pollutants where it has a clearly single identifiable source of pollution, such as the discharge point of a pipe or say a smokestack. So this is how we identify, the difference between these two things. And the distinction is that a non-point source pollutant, you don't really know exactly where it's from, and so you have to kind of treat a site. Basically, you have to avoid the creation of non-point source pollutants through keeping stormwater on a site. So some quick diagrams that kind of illustrate this idea. This is a watershed map of St. Louis, the downtown area of St. Louis. And then contrasting with that, this is the vegetative cover map of St. Louis. And what this also sort of illustrates in blue is areas of imperviousness. And so the combination of these two diagrams creates basically this image of St. Louis where all the water that's being shed off of the watershed and collecting into the basin is really collecting in the areas that have the least amount of pervious surfaces. And this is really, in a nutshell, the stormwater issue that we're dealing with. So you might have remembered earlier in the semester when I gave the lecture about stormwater, I talked about this question about how to cure an illness. And really, there were three trains of thought here. At the lowest level, it's simply treating the symptoms, pretending like the illness isn't there. At the second level, is about treating the illness itself, so like going to the doctor and paying for an expensive treatment. Then also, obviously, fixing the source of the illness, which is all about not getting sick to begin with. And so to do that, you need to actually change the way you live your life. And I use this because it actually is a good way to explain the various levels of stormwater management practices. So obviously, number one, hiding the symptoms. This is related to an outdated management practice where the train of thought was to get rid of stormwater and move it off the site as quickly and as efficiently as possible. You can see this illustration here of a drainage channel that's simply carrying water out of the city. But this is really an outdated philosophy. And so we really don't subscribe to this anymore. This idea of instead of treating the stormwater on site, getting rid of the stormwater, that's wrong. So we don't do this anymore because really this only multiplies the problem. Current practices, this is about treating the illness itself. This is mostly what we do currently. And this is about basically trying to keep as much stormwater on a site as possible, reducing the creation of stormwater and also the spread of pollutants across the city. So it's all about site scale BMP strategies in order to reduce runoff. In addition to this, there's also restrictions on floodplain development because of urbanization. Flooding is a major issue in cities. And so we have to think of ways that we don't create more issues for ourselves in terms of flooding. So related to floodplain development, there's something that you need to understand about that, which is this idea of no-rise certification. So FEMA, they manage and improve development that occurs within floodplains. And because flooding is a major concern in cities, basically you cannot do anything within a floodplain that creates elevated flood levels or raises the flood level. If your design or your development does that, you have to acquire a certification from FEMA that explains why increasing the flood height is good for the health, safety, and welfare of the public. And in almost all cases, there is no benefit to doing that. So that's why I write here, a project cannot increase flood heights. Increasing flood heights requires approval from FEMA, but it is rarely granted because, again, we don't want to create bigger issues for ourselves. But then at the bigger picture, how do we actually fix the source of the illness itself? And this is all about creating better planned cities. And so I'll call this the comprehensive and integrated approach to stormwater management. And so this is about addressing stormwater at the scale of the watershed, the big scale. And by doing so, what we're trying to do is we're trying to minimize the disruption of hydrology by maintaining pre-development drainage patterns on the site. It's about changing the way we develop cities in order to reduce the amount of hardscape that are out there. So there are these methods out there that I'm sure most of you have heard about. Urban planning in ways that reduce the amount of parking, cluster development, creating denser communities in order to preserve more open space and reduce the need for roads and parking, and TOD development, which is planning communities around public transit systems so that you reduce the reliance on cars. All these are methods that are designed to create the goal of reducing imperviousness on a site or a city scale. I mentioned these because actually all these things are things that are tested on the LARE exam. And so they might ask, for instance, like, what is the best case scenario for a TOD development versus other kinds of development? You kind of need to understand, where these types of developments really apply. Now, one random sidebar that, as I was putting together this presentation, it's worth thinking about. Right now, we have this COVID-19 coronavirus situation, which is really, really kind of creating a counter argument to this whole dense planning system right now, where basically, you look at New York City, which is really peaking in terms of the amount of illnesses and cases in America right now. It's a lot of the reason of that is because of the high density of New York City and the high population. In a way, you can say that creating these dense communities is also potentially creating a public health crisis should they say another virus comes along in the future. And so it would be interesting to kind of see where the profession of planning goes from here after this virus. Because, right now, what's in the media, what's in the news, people are saying like, stay away from people, spread out. It's really actually supporting the idea of more suburban style development. So it'll be interesting to see how the current health crisis is going to affect this idea of large scale planning. Moving along, we're going to now focus on the stormwater management strategies at the site scale. So this would be in that spectrum of how to treat the illness. This is the middle one, simply treating the illness itself. Site scale stormwater management strategies are really the bulk of what we try to do in our day-to-day practices, building technologies that improve the stormwater quality on sites before discharging it back into the earth. And so one of the basic things that we need to get familiar with is all the basic fundamental stormwater management systems that are out there. And so part of the exam will be to see how well you understand all the very fundamental systems of these. So we'll kind of cover all the major ones and explain what you need to understand about each one. The first one is obviously a simple swale. This is more of a grading solution than anything else. A grass swale, it's basically a constructed drainage channel that's used to direct runoff. Some pros, it's cheap, but that's mainly the only pro to that. But other than that, it's not very effective at removing pollutants. It can only treat a small volume of water. And since it's a grass swale, it requires mowing and maintenance and that kind of thing. So this is like a very basic suburban style stormwater management BMP strategy. Another one, and this is one that's very common in office districts and office parks, a retention basin, otherwise just simply known as a wet pond. This is a pond with a permanent pool of water. It always has water in it. And what it's doing is it's basically a pond that is a storage unit for stormwater. So when it rains, the water is collected and stored on a pond on site. And the nice things about this is obviously it's a pond, so it creates some nice aesthetic value for certain sites. It can create some habitat depending on where it's located. Sometimes people think ponds are a nice view, so it might increase in property values around it. So there's some potential benefits to having a retention pond around it. Some other aspects of it, it uses vegetation to treat the water quality, and it uses sedimentation to remove pollutants. Sedimentation basically means like as the water sits still, the sediment falls to the bottom of the pond, and that's how the water is basically cleans itself. So that's a retention pond, and that is contrasted with a detention basin or a dry basin. This is one important distinction to understand, is what the distinction between a retention basin and a detention basin. A detention basin, it's dry during non-rain events. These temporarily store runoff in order to control the peak discharge rate, and they are designed to be completely dry and completely empty during runoff events. So this image that you see on the right here, this is a detention basin during a non-rain event. So as you can see, it basically looks like a dry prairie planting area. This is nice because it does also serve habitat and prairie wildlife services, in addition to serving the stormwater management services. So again, another potential solution for stormwater management on site. The next one, a very heavily used system in landscape right now, infiltration basins. This is also known as a rain garden. Very, very similar to detention basins in that they store water during a storm event, but during non-flood events, they typically are dry. They need to be highly permeable in order to work. And so the planting that you see up here, it's all being planted within highly permeable soil that probably has a lot of sand content in it to create that permeability to it. Vegetation is the key to its success. It really needs deep rooting vegetation. What vegetation does is it basically takes up water, and then the fact that it takes up water increases the potential moisture capacity of the soil itself. So vegetation is super critical to the success of a stormwater. And obviously it needs water tolerant vegetation to work. It's a rain garden. So that's pretty much that. And then there is a simple sectional detail that shows what a rain garden might look like. You can see that in this particular one, it's using these gabion baskets here to act as a buffer and a filter for water that is being run off from the parking lot adjacent before it gets into this biodetention basin. Here's another example from another project that we worked on. Basically, see it's a very similar situation, whereas this one doesn't have the gabion basket filter. Instead, it uses a simple rain garden to do all that work for us. The next one, another similar strategy to an infiltration basin, is an infiltration trench. This is not designed with planting in it, but it basically has serves a similar purpose. This is also known as a French drain. It's basically a channel that is filled with coarse aggregate stone, and that aggregate stone provides a lot of open pore space which can be used to hold and store water in it. What's nice about this is it has a nice small footprint and can be integrated in combination with a lot of other stormwater BMP methods out there. Another strategy that we like to use are these sediment forebays. What basically this is a series of check dams where and each one stores water, and then during a high water event, it will basically allow water to basically rise and flood over the next check dam. And so it's basically creating a series of filters that is slowly cleaning the water. It's actually a very nice idea and a very nice aesthetic. We really like using check dams on projects because it's kind of like a dynamic rain garden that is cleaning the water during high water events. And also right here, what I'm seeing here is dissipation of energy from incoming stormwater. What these check dams here do is they basically slow the speed of water so that it can't just completely flush through this area. These check dams, they stop the water and then it slowly filters through to the next dam as it flows downstream. Porous pavement. So this is one that we use a lot in landscape. Obviously, you guys know what this is. It's about creating a stable walking surface or vehicular surface while increasing perviousness. There's various types of porous pavement. I'm going to show a couple after this slide. But there's two types of of porous pavement that we can consider. There's simply porous, which is to say that the water passes through the actual material itself. This is like, for instance, porous concrete or porous asphalt. And then there's non-porous solutions, which are solutions that create a design where there's actually spaces in between the paving that allow for water to pass through. So this is an example you see here, this series of paved steps with integrated green space in between. This is an example of non-porous pavement. So there's a lot of advantages and disadvantages. Advantages, it creates a higher recharge rate compared to natural conditions. It controls a lot of runoff, and it also helps reduce potential for swell and channel erosion, because again, what you're doing here is essentially you're reducing the need to, or reducing the creation of stormwater. So you're reducing a high velocity water that's potentially creating erosion on other parts of the site. Disadvantages, obviously, it's a constructed BMP that requires a high level of workmanship. So for instance, this one here, you can see it's basically a public garden. Probably didn't have the most, I guess, time or energy to put into the paving, but you can see here, like, it looks okay, but definitely could use a lot more workmanship in order to get a better quality look to it. So again, it is a lot more of a heavy installation cost in order to install porous pavement. This is an example of a highly professionally installed porous pavement parking lot. This is actually the parking lot at my office, and you can see here that it's a very, very simple system of interlocking pavers that sits on top of a permeable course of setting bed here. And so this is a nice example of a really, really well done permeable paving system. Then over here, this is an example of porous asphalt. And so you can see this is the distinction between porous asphalt and normal asphalt. You can see that with porous asphalt here, it's using essentially a single size of aggregate. And what a single size of aggregate does is it basically creates a lot of these open pockets in between the particles. And that creates larger pore spaces, which allows stormwater to penetrate through easier. So this is an example of a porous solution. This is an example of a non-porous solution to permeable paving. The next one is the green roof. And we all know about this. These are basically engineered roofing systems that are designed to support plants on our roofs of their buildings. What they're basically doing is they are reducing the amount of runoff from rooftops. If you think about it, a building is actually just a large impervious surface that is also creating stormwater runoff. So the green roof helps address that issue in a way. It has a lot of advantages that are more architecture related in terms of providing energy benefits to the building, and also creating potential recreational and aesthetic amenities as well that could be used in the building itself. And it's also one potential disadvantage is it's expensive to construct and also expensive to maintain as well. Now, actually, before we continue with stormwater management, I kind of want to cover everything about a green roof right now. So I just want to quickly talk about the types of green roofs that we need to understand. There's two types. First is the extensive green roof. This is basically a low maintenance green roof that contains a very shallow profile of soil. In here, I'm saying 2 to 6 inches of lightweight growing medium that usually is supporting drought tolerant species, usually sedums. So this is kind of like a very low maintenance, simple style of green roof. And that's contrasted with what's known as an intensive green roof. And this is basically an amenity deck, so to speak. So a lot of major cities where there's, say, a huge public aspect or maybe a hotel or something where having an amenity deck on the roof makes a lot of sense. This is where you have an intensive green roof. And in this case, you want to increase the amount of soil depth in order to support larger plantings, including trees as well. And so we do a lot of intensive green roofs as part of our practice, but one of the things that we also need to take consideration is the structural load that is on the support or on the structure of the building itself. And so usually when we do green roofs like this, you need to actually get the consultation of a structural engineer just to make sure that the things that we're proposing on that roof can actually be supported by the building structure itself. There's also what's known as a hybrid green roof, which combines aspects of both intensive and extensive systems. So you can see in the section here, It has aspects of, the more deep soil profile, but also the shallow soil profile that's supporting things like sedums as well. Another thing about green roofs that we need to understand are basically the simple basic components of a green roof. And so this is a list here. I'm not going to go through this list here, but just carefully study these things and just be aware that this actually is one of those critical details that you might be tested on the exam, which is basically asks like, what are the actual layers of a green roof? Now, what's interesting about this particular layer here is this layer right here called geofoam. I bring this one up since it's a it's actually a material that's being used a lot now in green roofs in order to create a lightweight grading solution. So instead of creating fill on the side that's heavy and would probably not be able to be supported by the green roof, nowadays projects are using this geofoam, this lightweight material, to create landforms and earthworks on sites, or not on sites, on green roofs, in order to be able to create more interesting landscapes. In this case here, this is Maggie Daly Park, a very nice park in Chicago that utilizes this geofoam in order to create the cool landforms and playground structures that are all across this area here. So again, this was a kind of a small aside that I took in order to basically explain all the aspects of the green roof. But now let's get back into stormwater BMPs. There's two more strategies that we've talked about in the class before. The first one, very simply, is rainwater harvesting, or obviously the use of rain barrels. This is basically just collecting stormwater on site and then using it for various other purposes, such as irrigation, as an example. It's cheap, it's cost effective, and there's really nothing else to say about that. It's pretty straightforward. And the next one is underground storage. This is one that not a standard landscape architecture solution, but it is a strategy that we have discussed many times in our office, and I think it's just one that you just need to be aware of. In instances, there might be situations where you might have a site that does not have enough space or area to build, say, a retention pond or a detention pond. And so in those cases, you might propose a underground storage strategy where they store stormwater below the parking lot or below, say, a sports field, which is a very common practice, especially, say, for instance, at universities. I would not be surprised if at WashU there was underground water storage at various parts of the campus. And so again, just another solution that we should have at our fingertips. And that should cover most of the stormwater BMPs that we need to understand. So I would highly recommend that not just looking at this lecture here, but also do the reading from the site engineering book, and also look through the stormwater BMP PDF on Box, which actually has a good detailed explanation of a lot of other various BMP systems. So next up is soils. Pretty obvious, soils is one of the more important components of being a landscape architect. If we look at all of the skills that a landscape architect needs to have and what they do in their day-to-day job, every single one of these things relates to soil in some manner or fashion. And so this list here very clearly illustrates, for everything that we need to do in our day-to-day work, there is some type of soil science that relates to that. So, with that being said, what is soil? Soil, and this is just a scientific definition, a soil is an accumulation of solid particles generated from the physical and chemical weathering of rock, containing a network of voids that may be filled with air or water. Soil is therefore comprised of solid, air, and water. This is the USDA textural classification system. This is how we understand the different types of soil that we might specify on a project or we might find on a site. And it's basically designating soil as a breakdown of three major particle size groups: sand, silt, and clay. The main thing that you just need to remember is sand is the biggest particle size, silt the next biggest, and clay is the smallest particle size within this mixture. And so what the soil textural triangle here shows is basically 12 designations And the way that you might read a soil texture triangle is you want to always like start with, say for instance, let's say we want to like designate clay loam here. That one would be 30% clay, 30% silt, and 40% sand. And so that adds up to 100%, and that gives you the designation for clay loam. And so I might ask on the exam, for instance, what is some percent of clay, some percent of silt, and some percent of sand? And you should be able to read a soil texture triangle and be able to tell us what type of soil is at that designation. Another part of soil that we need to understand is soil pH. And so this is basically measuring the acidity or the basicity of soil. This usually ranges between 0 and 14, with below 7 being acidic and above 7 being basic. The optimum soil pH for most plants is between 6 to 7.5, though many plants will survive out of this plant range depending on where you are actually working in. These two things, the soil textural classification and the soil pH, these are things that we need to specify in a soil specification. And so a typical soil specification will define a growing medium as a predefined mix of soil, topsoil, sand, and compost. And it'll usually give you a percentage of each of these components, in addition to also describing the soil textural designation, as well as a potential soil pH for other growing medium. This mix of these elements here really is determined on where that soil is being used. Say, for instance, on a green roof, there might be more sand and more compost in order to increase the porosity of the mix and decrease the weight of it, because these elements actually decrease the density of soil. And so depending on where it is, you might specify soil in a different way. And the picture that I'm showing on the right here is an example of a soil submittal. So basically during construction, the contractor will usually send the landscape architect a bag of soil and any additives as well in order for us to approve that submittal. Like this is, if this is correct for what we want to add to the site. And as a landscape architect, our job is to either approve it or disapprove it, depending if it's not meeting the specification that we asked for. Okay, some definitions. Bearing capacity. Bearing capacity is the maximum load or weight that a soil is able to support. It's usually expressed in pounds per square foot. If the bearing capacity of an existing soil cannot support a proposed load, then that soil must be removed and replaced with a suitable material. So bearing capacity, it's a really important concept that we'll bring up again a couple times in this presentation. Compaction. Compaction is exactly what it sounds like. It's the compaction of soil, which increases the density by decreasing the amount of void space in soil. Compacting soil increases bearing capacity and shear strength, but obviously compacted soil is bad for root growth. Again, this is a pretty major issue that we'll talk about several times. Structural soil. This is a special engineered type of soil that's used specifically in situations where there requires a high level of compaction on site. This is gap-graded angular crushed stone designed to have a high bearing capacity while also supporting tree root growth. So if we go back up here, you remember where we said basically compacted soil is not good for root growth? This is a system that is designed to kind of go around that. What this basically is doing is that it's using gap-graded crushed stone here. What that basically means is that there is no mid-sized stone here. So you see there's large particle sizes and then small particle sizes, but there's no mid-range particle sizes. And what this is basically doing is it's creating a lot of pore space in between the large stones, which is being used with this, filled with this lightweight soil medium in here that could be used for root growth. And all the weight from the compaction is being supported by the actual larger particle sizes. This is a soil specification that's being used a lot in urban conditions now. Though one note I will say is that this is not, at the end of the day, a replacement for normal soil. And we should be designing projects with the intention of using non-structural soil as much as we can before we have to actually end up relying on this technology. It is expensive. That's one thing to note as well. Like, obviously, if you, it's not to say like, oh, compaction to prevent it, let's just use structural soil everywhere. This is not the fix all solution that that we think it is, though it is one technology that we can use. Structural soil, what it's doing basically is it's increasing the amount of soil volume for trees on sites. So this is an example of a site section for a structural soil where basically we're showing that the growing medium for the trees is pretty much the entire width of the sidewalk, whereas in typical urban conditions, it would only be at the actual tree trunk section itself. But with structural soil, it allows a greater amount of tree growth. So that's a little bit about that. But then another technology that's being used to mitigate the effects of compaction are these modular support systems known as Silva cells. So this is a support system that's being used to support paving or vehicular traffic. And it's also similar to structural soil in that it's actually really designed to promote root growth through the pore spaces in here and not create a situation where there's a lot of soil compaction on site. A quick layout plan showing a plaza space that utilizes Silva cells in integration with a series of tree root holes here. Another type of structural soil that can be created is what's known as turf grid reinforcement. Basically, we mix in these fibers into soils, and what actually it does is that mix increases the bearing capacity of soil. And so mixing this into a soil creates a form of structural soil that is sometimes used on sites as well. And then another definition that's important to understand is shear strength. Shear strength is basically the ability of soil to resist failure under loading. This is important because shear strength determines the steepness that a slope may be graded without constructing a retaining wall. A retaining wall will be necessary in areas where the shear strength is too great, and it will create a condition like this where there will be a failure in the slopes. And so in the case of that, you will need to add a retaining wall to protect a slope. There are two ways that shear strength is created. It's either through internal friction. Internal friction basically means that the particles are grabbing onto one another through the size of their particles. And so, for instance, sand and gravel have high internal friction. The other one is cohesion. Cohesion is basically the attraction of particles due to the moisture content within the particles. And so, for instance, clay has high cohesion. And so two methods or rather two types of soil grades that determine its shear strength. So related to that is what's known as an angle of repose. This is a test to really test the shear strength of soil. The angle of repose is basically the steepest angle of descent where the material on the slope is on the verge of sliding. And so this is a test to basically understand, for instance, what is the steepest angle material of this type can be graded towards before it begins to erode and slide off of site. Another major definition is frost depth. This is basically the depth to which water in soil freezes. This is important because it impacts the depth of foundations. So foundations for things like retaining walls or stairs or piers as well. Foundations we design in cities and sites should always be below the frost line in order to avoid this phenomenon known as frost heave, which creates a lot of damage to roads and structures when it happens. The frost depth varies by region, as you can see by this map on the side, which shows the frost depth from the south to the north, where in the north the frost depth is much deeper due to the lower temperatures up in the north. Topsoil stripping, this is a method of, or rather a phase of the construction where soil on sites, the topsoil on a site is stockpiled during grading. Basically, the topsoil on an existing site is really valuable. It's really organic rich, and it's something that we don't want to waste. We want to reuse it at the end of the construction process. So topsoil stripping is removing that and stockpiling it off to the side of it. Soil that's stockpiled for an extended period should be seeded in order to prevent erosions. And under ideal conditions, topsoil will not be stockpiled for longer than 6 months and will not be piled higher than 4 feet. The next major topic is erosion and sediment control. So you might remember from the stormwater management chapter where we talked about non-point source pollutants. The biggest non-point source pollutant is actually sediment that is created by erosion. And so actually during construction of projects where a lot of soil and silt gets eroded off of the site, that is what's being washed into our water bodies through stormwater runoff. And so that's why erosion and sediment control is a big deal and an important aspect of soil sciences that we need to understand. The definition of erosion, it is the deposition of soil by action of water, ice, wind, and gravity. And as I said, by volume, sediment from erosion is the largest non-point water pollutant. Erosion control are measures which are used to reduce the amount of soil particles that are carried off of a land area through things like stormwater runoff. And so these measures should prevent runoff from off-site areas from flowing across disturbed areas. And they should also remove sediment from off-site runoff before it leaves the site. So I'm going to go through a couple of erosion control technologies, but you should also refer to the sediment and erosion control PDF that I saved on Box for a long list of examples that you need to understand. So the most effective way to control erosion on the site is actually simply through the use of vegetation. A few reasons for this. Number one, it shields the soil surface from rainfall. Secondly, it decreases the speed of surface flow. So you imagine water shedding across a surface. Planting a vegetation actually mitigates and slows down the speed of water. Vegetation, it restrains soil movement. So the roots themselves are actually holding the soil in place. It increases infiltration rates by improving the soil structure. And also vegetation takes up water in soil, which increases soil moisture capacity. So you remember I said back in the rain garden section where basically these plants, they're taking up water. And what that basically is doing is increasing the capacity for that soil to take on more or hold more water because of that. Now, obviously, one thing to take into account is that to seed a slope, it requires very good climate and weather in order for the plants to establish. And obviously, in order to establish plants, you need a lot of irrigation for it to successfully grow and establish. So those are just some constraints and considerations that need to be taken into account when using this method. Geotextiles. This is quite simply a use of a filter fabric, such as synthetic fabric or construction fabric, in order to create a matting to basically protect the slopes of a hill from erosion. A very simple way to do that. Chemical stabilization. This was a simple, if you guys remember from the lecture, I talked about this rooftop example in Clayton, where they had these roof gardens which were dealing with a lot of wind erosion because of the fact it's a roof garden. And so one of the solutions that was suggested was to use actually this chemical stabilization technique, a type of soil binder that is sprayed onto the surface of the soil in order to hold it in place. Obviously, this actually might create some harmful effects in terms of the soil quality and of the water quality if not used correctly. So I haven't used this ever before, but it seems like I wouldn't know how to use this one, but it's one of the tools that we have at our fingertips to control erosion. Sodding. This is actually a pretty fun one. This picture here is of the design and build project that I worked on when I was at undergrad at WashU. Sodding, what that basically does is that it covers the surface of a slope with vegetation immediately, and it provides immediate erosion control. In a way, the sodding is not too dissimilar from a geotextile matting, except this is a plant, but it's a mat. And so one of the things that needs to be taken into account is that this does require a lot of irrigation and initial installation costs uh, use, but it does look cool, and it does create a usable site almost instantaneously when applied. One note I'm having here is that whenever you do this method, you always want to lay out your sod sheets in a staggered pattern, kind of almost like a running bond pattern in a paving. And then you also need to hold these in place using stakes of some kind that hold this in place. A silt fence, this is a method that's used a lot during construction projects. This is a temporary measure that's being used to basically control the runoff of silt on a site. If installed improperly, this can fail easily, but when it is used, it's a fairly effective and inexpensive way to control erosion on construction sites. This is an example of a silt fence. It's a fiber roll. So I referenced this detail several times in class where basically there was a situation where we had a detention basin, and because the detention basin was installed incorrectly with poor erosion control, actually when construction finished, the detention basin failed because it actually filled with silt. It wasn't properly protected from erosion during construction. And so what we did was we proposed this modified erosion control detail where we actually put a couple of fiber rolls in addition to some mats on the ground in order to control the silt so that it would not affect the detention basin. Earthwork. So this is kind of going back to some concepts that we talked about in grading and landform class, but just good review for us to understand. Cut and fill. So cut, you know this already. It's removing soil. Fill, adding soil. A key point here is that in situations where you cannot balance cut and fill, it is generally better to use more cut than fill, simply because importing soils, bringing soils on the site, you have to buy that soil, you have to bring the soil onto the site, and that ends up being a higher cost than simply removing soil on the site. And then the other issue is that a fill condition is usually structurally less stable and more susceptible to erosion and settlement. Basically, when you put new soil on a site, there is a tendency for it to settle and to not have the density that it needs to be at finished condition. So in situations where you cannot balance cut and fill, generally speaking, this is not necessarily a thing that's agreed upon by everybody, but I would say some kind of a rule of thumb. In situations where you cannot balance cut and fill, generally better to use more cut instead of fill. And then lastly, one thing I just wanted to quickly go over was the basic terminology that you need to understand in terms of a standard soil section. So finished grade, this is literally the surface elevation that we designed to. This is the completed surface of lawns, walks, and roads brought to the grades as we designed it. Related to that is also the finished floor elevation. This is more related to the ground floor or any floor of a building where pedestrian traffic exists, the finished floor elevation. And this is really important because usually when we design projects, our landscape projects related to architecture, we always want to make sure that the exterior grades meet the FFE, the finished floor elevation, in order for people to, obviously access the site from inside to outside. Base or sub-base, this is usually some kind of imported material that is placed under pavement. Usually it's some kind of gravel or aggregate. This is usually the immediate material right below the material that's being used to create the finished grading. And then the compacted subgrade. This is the existing soil on site that's compacted in order to achieve a specific bearing capacity to support all the additional elements that we are adding onto the site. And in addition to compacted subgrade, there's also undisturbed subgrade. This is simply soil that we don't compact. We just simply it's simply the area that we don't need to do anything to in order to prepare the site. So that is basically all of soil in a nutshell. I would highly recommend that everyone do the Strom readings, the readings from the site engineering book on the soil chapters. That does a pretty good job of explaining everything that you need to understand in terms of understanding soil. And I also highly recommend that everyone also learn how to read a USDA soil texture triangle, because that's something that I'm going to test on the final exam. Next is parking and ADA. ADA is the Americans with Disabilities Act. The ADA mandates policies, procedures, and practices that provide equitable access for all people to jobs, buildings, services, transportation, and other aspects of everyday life. When we think of ADA, what we're really talking about are people with special needs. Say they have hearing issues or they need to ride a wheelchair. And really what ADA is promoting is the concept of universal design. Universal design means basically that our design projects should work well for everyone of all users and abilities, so that everyone gets the same quality of experience when they're actually entering our projects. The group that really approves these projects, there is an organization within the St. Louis City called the St. Louis Office of Disabled, who go on public projects and they really approve and advise how to best make projects accessible, especially for wheelchair users. The example that most recently happened on our end is that we had a project that had unit paving, and the Office of Disabled really asked us to look at Keener Plaza, the new plaza that was just built in downtown St. Louis. The main reason being is that because there is no beveled edge to the paving here, this actually creates a very smooth experience if you are riding across this on a wheelchair. This contrasts with a more standard looking paving pattern, where every single paver actually has what's known as a bevel. So you can look closely here, you see that there actually is a little chamfer. This is known as a bevel on the edges of the paving. What this does is actually, if you ride a wheelchair across this, you can imagine there's actually a bit of a rumbling effect to it. And so the compromise that we made with the Office of Disabled was to suggest that we actually run the paving, the bond of the paving, in the direction of travel, so that the long end matches the direction of pedestrian movement. And this is a good way to reduce and minimize the rumbling effect if you're going to ride over a plaza using a wheelchair. So now we're going to get into a little bit of an ADA review. These are design concepts that you probably have come across already at some point in your design education, but it's really important that we reinforce these concepts so that you always have these numbers and these dimensions at your fingertips whenever you're working on your own projects. The first one is the minimum width of a walking surface. That is 36 inches. 36 inches is important because that is the minimum width that a wheelchair user can safely move across your path. If you want to have a pedestrian in the opposite direction past the wheelchair, you need at least 48 inches. And if you want to have two wheelchair users safely pass each other, you need at least 60 inches. And actually, I would say in general, the recommended width of a walking path should in fact be around 60 inches or more than that, simply because it allows this simple access where two wheelchair users can pass one another. The maximum slope of a walkway is 5%. So basically, a walkway can be defined as a pedestrian path that does not require any landings or a handrail. If you go above 5% and up to 8.33%, then you have what's known as a ramp. So a ramp is between 5 and 8.33%. With a ramp, the maximum run of a ramp is always going to be 30 feet. So after 30 feet, you're going to need to have a landing, a flat landing for that ADA ramp. The maximum cross slope of a walkway or a ramp is 2%. Cross slope being the direction of slope perpendicular to the direction of travel. So this is the direction of travel. The cross slope is this one right here, and that slope cannot exceed 2%. Beyond 2%, that's when it actually becomes noticeable that there is a slope and becomes a little bit uncomfortable for the user. Ramps that change direction between runs at landings shall have a clear landing of 60 inches by 60 inches. What that means is basically, you see this diagram here, this ramp makes a turn at this corner right here. This landing here needs to be at least 60 inches by 60 inches in size. The reason for this is actually, we can explain that in a few slides back. You see here, basically, If a wheelchair user needs to make a turn, they need at least that 60-inch by 60-inch box to make that turn. So that's why we need to provide that at a turn of a landing. Handrails need to extend at least 12 inches beyond the top and bottom of ramp runs. So this is the ramp right here, and then 12 inches beyond that, you extend the handrail, and then 12 inches beyond that, you extend the handrail again. Where curbs and rails are installed, ensure that the height and configuration of the barrier prevents the passage of a 4-inch diameter sphere where any portion of the sphere is within 4 inches of the ramp or landing surface. So basically, look at these two examples here. You see, this is the ramp surface here. In this top example here, it's basically providing a 4-inch high curb from the surface of the ramp, so that a 4-inch sphere obviously cannot come through the side of it. And then here, instead of doing that, it's providing another railing at the bottom here that prevents the passage of a 4-inch sphere through here as well. Ramps should generally have the same starting and ending location as stairs. So here's an example. Basically, this is going back to the concept of universal design, where we want to provide the same experience to all users. So obviously, if you imagine a person and a wheelchair user coming to this transition point here, you want to make sure that they start at the same location and end at the same location, so they have the same experience and they don't have such a different, like you, for instance, you might not want to give the wheelchair users a completely different pedestrian path experience from the person who can take the stairs. So this is a good rule of thumb to keep in mind when you're designing ramps on your projects. Now we're going to get to a little bit about parking. Parking is really just about understanding the basic minimum dimensions of a parking stall. So a parking stall, it comes at these various angles here: 90 degrees, 75 degrees, 60 degrees, 45 degrees. And really what's most important is simply remembering the actual dimension of a typical parking stall and the backout dimension. The main one that we mainly use is simply the right angle parking dimension, which has a 9-foot parking stall width and an 18-foot long parking stall width, and you need at least a backout distance of 24 feet. When we're designing parking lots, we always design parking lots at these 120-foot, actually this should be 120, these 120-foot bays, because this is kind of a way you pack in parking onto a site. A 120-foot bay is a very standard massing dimension that we use to mass out these parking lots. A single bay would be a 60-foot dimension. So whenever you're planning your project, always, or rather you're planning a parking lot, always try to like block it out in terms of these dimensions, and it's a very easy way to lay out a lot. This diagram here just basically illustrates all of the basic parking lot components. I don't need to speak through this, but you can study this and understand what are the basic design elements of a parking lot. What's somewhat important to understand, though, is that we need to understand how do we get to a number of parking requirements, and this is established by every city's zoning code. And so the zoning code will basically explain how much parking do you need for a specific land use or building use. For instance, the top example here is showing that if it's an office building, you need at least 3 1/3 spaces for every 1,000 square foot of gross floor area. And for every other thing, whether it's a recreational use or residential use, it's going to have some kind of a zoning requirement in terms of parking. So that's how we figure out how much parking a project needs. And then also what's important to understand is how can you calculate the number of accessible stalls required for your parking lot. And so there is a chart here that basically you need to remember in order to figure that out. I remembered this when I took the LARE, and they will literally give you an example of this many parking spaces, how many accessible spaces do you need in order to make this parking lot accessible. Actually, what I will do is I don't think I'm going to make you guys remember this, because I don't even remember this myself. This is a chart that you can have, next to your desk whenever you're designing anyway. For the exam, I will simply supply this chart for you guys and just ask if you have a parking lot of, say, 500 spaces. You just need to be able to tell me that it requires 9 accessible stalls. So that's basically all this is. But then one important ADA note is that when you do have an accessible stall, you always want to make sure that you have a 5-foot minimum width parking aisle at one end of the stall here. So you see these examples here. These are two accessible stalls and they share a single accessible aisle in the middle, like so. And that's basically all I really want to cover in terms of parking and ADA. It's pretty straightforward stuff. And I don't really want to bog down on, honestly, parking in general. It's not the most interesting or fascinating design challenge in my opinion. You'll have so many opportunities to design parking lots in your day-to-day job when you actually get out of school. So you can worry about that stuff at that point when you get to that point. The last major section that we need to talk about for this class is landscape detail. Now, this is a bit of a unique section in that it's something that I would highly recommend you actually do study and do look at the readings for in more detail than the other parts of this video, mainly because I'm going to be testing actual details themselves, and it really is important that you guys know some really basic details that you can use on your projects. So how to study for this part, here's what I'm doing. Here's my recommendation. Review this video, but also review the readings. The exam is not going to test specific or detailed information regarding material sizes, but it is going to test a minimum level of understanding on common standard details that are used throughout landscape. You should be able to look at a detail and label the typical materials used in constructing the design detail. This is a question that was actually on last year's exam, where basically I gave every student a detail, but left the annotations for the materials blank. And so your job would be to basically annotate and notate what each of these materials are. And so you should be able to look at this and understand what each one is going to be. This is actually a fairly basic detail, and it's very common across most of landscape. So that's my recommendation on how to study for this part. We're going to break the detail down using the diagnostic site section. This is the assignment 2 from our class, but actually this was a concept that was researched and brought to me by Neil Kirkwood, who was my professor of this subject back at Harvard. And so he described every detail as being able to be categorized within either a boundary, a surface, or a transition. And then there's also the site object, which is not the most important one. Really, it's boundary, surface, and surface transition. And we can define every detail within one of these major buckets. So important to do is you got to be able to look at a detail and be able to also to label what type of detail it is. Is it a boundary? Is it a surface? Or is it a transition? So we're going to go through a couple of standard details in this video, but again, I still highly recommend that everyone use the time savers resource that I saved in a box to actually look at some very specific drawings of details in order to prepare for this exam. So the first type of boundary, pretty obvious, is a freestanding wall, right? A wall is a basic boundary. All walls require foundations, and every foundation needs to be below grade and below the frost line. We talked about the frost line earlier in this presentation, and you already know why. A wall is always comprised of a base, middle, and top, and it can be cladded in stone, concrete, brick, wood, or even metal. Cladding can either be rendered on a structural core through fluid coating. So imagine, say, we applied the brick to this wall using cement. It can also be hung, say, in this example right here, we have a concrete core, and then we use metal anchors that actually hang, say, if it's a stone veneer, onto this wall here. You should take a look at some of the details that are on time savers in order to really fully understand what that is, what that means. Retaining walls. Retaining walls is a heavily tested detail on the actual LARE exam. And so actually, when people prepare for that, you basically need to remember how every single type of retaining wall is built and constructed, because you don't know what type of retaining wall will suddenly pop up on the exam. So I'm going to show a couple here, but definitely look through the retaining wall PDF that I saved in a box in order to get a better idea of how the various types of retaining walls are built in landscape. First one is a very simple one, which is the unit block wall. This is usually made of stone or precast concrete. It uses interlocking units that, through the use of their weight and keyways, the keyways are these little notches here, that can prevent overturning from the force of earth that it is retaining. And it's usually battered at an angle in order to enhance stability. What I mean by that is basically this angle right here. that is what we do in order to improve the stability of this wall. The vertical cantilever wall. This is the most common type of retaining wall that we see in landscape architecture. It consists of a horizontal reinforced concrete foundation with a vertical reinforced concrete wall. So the horizontal foundation is this guy, and the wall is that guy right there. The section of this wall usually appears as an inverted T, as you can see right here. This works on the principles of leverage to retain the earth. And also this is similar to the freestanding wall in the sense that it can be clad with any kind of material such as marble, stone, anything else. In this example here, this is the Vietnam War Memorial, which has these amazing looking granite panels that are hung on this concrete wall. This is the most common type of retaining wall that we work with in landscape. Then last is the gabion wall. This is also one that we use quite a lot in our practice. These are simply just basically woven wire baskets that are filled with broken rock and are stacked on top of each other in order to retain soil. Okay, so moving on to the next category beyond walls is surfaces. So the most common type of surface that we use is the reinforced concrete surface. We also call this concrete paving. This is a type of paving that's installed over compacted crushed gravel. The thickness of your concrete is dependent on the anticipated uses and loads of the surface. And you're going to need to put expansion joints every 30 feet and control joints every 10 feet plus or minus in order to make this concrete paving work. And it can vary in finishes. This is a plan for a little plaza that we designed out in Pennsylvania, where we're showing a variety of finishes on this concrete. You can see all these different hatches here, where these hatches are actually indicating our different finishes to the concrete. Speaking of expansion and control joints, this is pretty important to understand. These must be used or must be added to every single piece of concrete slab that you design, because concrete, through weather and temperature changes, will have to crack at some point. And so what we do is we add these joints in order to control the location of cracking from that change in temperature. So expansion joints, they should occur where a structure meets a pavement or differing pavement meets an expansion joint. This is what that is right here. This is what's known as a full depth joint. So basically that means is that the joint cuts through the full length of the paving. It breaks it entirely. This is subtly different from a control joint, which is mainly just a small minor incision, a minor cut along the paving that's added after the slab is poured. And again, this is what this is doing, is a controlling crack. You see in this illustration here, it's actually illustrating that crack right there. So the control joint is providing that weakened area for that crack to occur. Asphalt. So asphalt is obviously one of the more common paving materials that we see in cities now. It's what's being used to pave our roads. It's what's being used to pave parking lots. Asphalt, it's a mixture of bitumen and aggregate positioned in layers. Bitumen is basically a type of binder that binds this aggregate together to create what we know as asphalt. We use compacted crushed rock as the typical subgrade material, and we need to have an edge restraint in order to have to create a asphalt surface. So for example, in this one here, we're showing this concrete curb at the edges of this greenway here. Crushed stone or gravel. This is basically stone that has been crushed to a specified diameter and then compacted during installation. What's important is that since it's basically a loose material, it will spread out if there is no edge restraint or edging installed with it. So this example that I'm showing right here has a curb that's flush with the surface, but really what it's doing is it's providing that edging to prevent the spread of this material when it's being used. Unit paving surfaces. So the most common type of unit paving that we use in landscape architecture is precast concrete paving. This can come in a wide range of sizes, shapes, colors, and finishes, which makes them a great design tool for us. When we are installing paving, it always requires what's known as a sand setting bed. That is this little profile in the section detail right there. And the sand setting bed, its job is basically to level out any irregularities that come about when installing the pavers on the project. Another type of setting bed that might be used is an asphalt setting bed with an adhesive tack coat. Well, we use this if we want the paving to actually have a more rigid feel when you're walking across that surface. We like to use concrete pavers because they have high durability, which makes them appropriate for both pedestrian and vehicular traffic. There are various types of paving out there, including brick paving, stone paving, granite paving, marble paving. But generally speaking, all the paving have basically the same detail where you have the surface that's sitting on top of a sand setting bed and on top of a reinforced concrete slab and on top of a compacted aggregate base. Depending on what type of paving you use, but you're always going to need to have some kind of paving plan to go with it. And so this is an example that I'm showing here is from the paving plan for Keener Plaza. This was used by the contractor to help them install this really interesting specular paving pattern that he used out here. And really all this is doing is just to provide a tool for the contractor so they can install pavers on site with accuracy and with little error. There's a few type of paving patterns that you need to understand and remember. The main ones that I think are important to remember are the basket weave, the herringbone pattern, and the running bond pattern. This is stuff that's actually tested on the LERE exam, and so you just need to remember what they look like. The basket weave is the one that I joked about during class that looks really old-fashioned and ugly, and I don't like this one because we have to use this on a project due to its look, and so whatever. And last but not least, in terms of the categories of details, is transitions. So the most common type of transition is the curb. The curb is basically what negotiates the elevation change from, say, a street to a sidewalk. So a curb, a typical street curb, is basically 6 inches wide and 6 inches high. The entire construction of the curb is actually 18 inches and is laid on top of a concrete foundation. The height of this curb here usually varies from flush meaning that it's flush with both the road surface and the adjacent surface, to about 12 inches. But once you go beyond 12 inches, actually the definition of the curb changes and it becomes a seat wall. So at about 18 inches, this becomes at a height that is comfortable to sit on, and that is why we call what we call a seat wall. And then when we go beyond 30 inches, then we're creating essentially a retaining wall. So then at 30 inches, it no longer becomes something that is comfortable to sit on. It becomes more of a wall used for retaining. So there's a lot of types of curbs out there, and what you need to know is basically this is your basic type of transition that we use in landscape. The next type of transition, obviously, is the stair. The stair, if you guys remember from grading and landform, we have this stair comfort calculator where basically in order to get the right ratio of tread width to riser height, you usually want to do it with a 2 times riser plus tread inch equals 26 inches. This is just kind of a rule of thumb, not a hard and fast rule. Really what this means basically is that, when we're doing this kind of detail here, figuring out those dimensions, it really requires a lifetime of experience and practice to figure out what is comfortable. It's all about just creating a simple, comfortable walking experience for users. So a lot of stair details are generally similar, but it usually consists of a concrete foundation with stone or granite treads that are laid on top of a setting bed. It could also be entirely poured out of concrete as one giant precast piece. And in terms of accessibility, a flight of stairs should usually always have a maximum vertical flight of 5 feet before requiring a landing. And then the last detail in terms of transition are ramps. Ramps are very common. We just talked about ADA ramps previously. So a ramp is defined as something that's sloped between 5% to 8.33%. Again, refer back to the ADA chapter to talk about the requirements in terms of landing needs. And the construction sections for ramps, the paving section for ramps, is generally very similar to the sections used for paving patterns and stairs. So there isn't that much to it. This is more of a grading detail more than a construction detail. So yeah, that's ramps. And that is the end of the review guide. So I would highly recommend all the students after this point maybe go back to the box folder and actually look at the readings that I used to put this presentation together. Again, everything that's in the presentation that I just showed you guys is stuff that is on box right now. And the best way to honestly study for this exam is to look at the readings on box and study them. For the detail section, highly recommend that you guys look at this resource right here, Time Savers Standards for Landscape Architecture. This is the best resource to understand a lot about landscape architecture. And then also for site engineering concepts, read the Strom reading right there. I've saved a couple of Strom readings on box and also in these various folders here as well. So with that being said, I appreciate you guys sticking around and listening to this long lecture, and I will talk to you guys soon. Good luck and study well. Thank you very much.